Okay, when we left off last time, I said to you, answer these questions on your own and then do some practice problems in live worksheets. And that we would pick up here next time and we would go over these answers. Okay. What does acceleration measure? Acceleration measures a change in velocity's rate, or a change in the rate of velocity. Okay, now it's important to remember that velocity is speed or direction. So if either speed or direction changes, the velocity is changing. The acceleration is changing. It says compare and contrast positive and negative acceleration. Both positive and negative acceleration measure a change in speed. Positive would be an increase in speed, and negative would be a decrease in speed. So again, you can be accelerating. It's negative acceleration when you're slowing down. It's positive acceleration when you're speeding up. And it's also acceleration when you're changing direction, which leads us right into question 3. When is an object accelerating? When it is speeding up, when it is slowing down, or when it is changing direction. Speeding up, positive acceleration; slowing down, negative acceleration, and changing direction. What's the formula for calculating acceleration? It's the ending velocity minus the beginning velocity divided by the time to change the velocity. Now, again, okay, it's a general concept. If you have to calculate the change in anything, it's always the ending minus the beginning. Okay, here's the example problem. Okay, it says a car went from 15 meters per second to 5 meters per second in 3 seconds. What is the car's acceleration? When we read this, the car started at 15 and it went to 5. So 15 is the beginning. That's what it started off at. And it goes to 5. So first off, we should notice that the car is slowing down. So it's going to have negative acceleration. It's going to have a decrease in speed. So we're going to plug these numbers into the formula. Okay. The ending is 5, so it comes first, minus the beginning, which is 15, divided by the time it took, which was the 3 seconds. So 5 minus 15 is negative 10 meters per second, and it took 3 seconds. Again, notice there's 2 units of time, meters per second, and then this fraction bar means divided by seconds, so it's meters per second per second. When we do the math, okay, 10 divided by 3 is negative 3.3, and our unit is meters per second squared, or meters per second per second. Notice that the acceleration is negative. That is because the car slowed down from 15 to 5 meters per second. Okay, now, we've been talking about things moving. They have speed, they have motion. Okay? We haven't talked about how they get moving. Well, it's forces. So forces are directly related to that. That things are moving. The first definition for today is the definition of a force. Force is a push or a pull that one body applies to another. Now in physics, when they say a body, they don't mean like, a living thing. A body is just anything. So like the earth is a body. A car is a body. A baseball bat is a body. Applying it to another body would be like baseball. So it's just when one thing applies a force to another thing. In physics, they always call it a body because that's what Newton called it. Okay? And speaking of Newton, forces are measured in newtons, which is just an N. So, since he was the one who did the original work about the idea of forces, they named the unit for force after him. When 2 or more forces combine at the same time, they create a net force. Okay? Net means sum. This is important. So it's the sum of all the forces acting on an object. Very rarely, and I really can't think of many examples, if any, where there's just one force acting on something. So there's almost always more than one force acting on something. So if you add them all together, you get the net force. Like, so as they all, some of them add together, some of them cancel out. This is like the net. So even for example, me sitting here in this chair, gravity is a force pulling me towards the earth. Something is holding me up from falling to the earth, which is the chair. The chair is pushing up on me. So the gravity is pulling me towards the earth, and I would, if the chair wasn't there to overcome the gravity, I would fall out of the seat onto the floor. So the bottom of the chair is pushing up. So I'm pushing down on the chair and the chair is pushing back up on me. So a total of all the forces. Okay. Forces are what can change an object's motion. So that's how it's related to this unit. Obviously, if you push or pull on something, it's going to change its motion. Okay. The arrows tell us two things when we look at these arrows. The forces are usually going to be represented by these arrows. And they tell us two things. One, they tell us the size of the force. So the bigger the arrow, the bigger the force. The other thing they tell us is the direction of the force. So in this example down here, it shows one force pushing to the left with 3 newtons and one force pushing to the right with 3 newtons. Okay, so we have the direction of the force. The arrows are the same size, so it indicates that the size of the force is the same, and these also happen to be like 3 newtons. So it shows that this has a net force of 0. That's because they're balanced. This force to the right is going to be canceled out by this force to the left. And you have to ask yourself if they were pushing on something where it moved. Well, if they cancel out and the net is 0, 0 means 0, so nothing's going to happen. So that's the next thing we're going to put in the notes. Balanced forces are equal in size and opposite in direction, just like these two down here. They're equal in size, they're both 3 newtons, and they're in opposite directions. One's pushing to the left and one's pushing to the right. When this happens, because the net, the total is 0, and they cancel out, there's no change in motion. If the object is moving, it'll stay moving. If it's still, it will stay still. So if something was moving and you pushed on it from both sides, it would just keep doing whatever it was doing. Or if it wasn't moving, like me sitting in the chair is pushing up, I'm pushing down on the chair. It's a balanced force because the chair is able to push up on me equal to what gravity is pulling me towards the earth, and I'm pushing down on the chair. It's balanced, so there's no motion. I don't fall to the earth. If the weight pushing down on the chair became greater than what the chair could push back, the chair would be crushed, it would be unbalanced, and I would fall to the ground. Okay, so balanced forces, okay, I put balance over here so you can think about them. They're equal in size, so they're going to balance each other. They're opposite in direction, so the balance isn't going to move. It's just going to stay in the same place. There's going to be no motion when they're balanced. Okay. All right. Now, unbalanced forces are exactly that. They're not balanced, okay? Because they're not balanced, okay, they're not equal. The balance is going to move one way or the other. So they're going to cause motion. So unbalanced forces are unequal in size and or the same direction. Okay? This will cause a change in motion. Okay? So they're unequal in size and in the same direction. So we have this 2 Newton force plus this 3 Newton force. They add together to make a force of 5 newtons pushing towards the right. They can be unequal in size and in opposite directions. So again, the forces add together. So in this first example, the 2 original forces, this 2 newtons plus 3 newtons adds together to make a 5 Newton force pushing to the right. So this might be an example of 2 people pushing on a car. One person pushes with a force of 2 newtons, the other person pushes with a force of 3 newtons. Their combined force of how they're pushing on the car would be 5 newtons. Okay. And they're unequal in size in opposite directions. They're going in the opposite direction. So in this case, you have 2 newtons going to the right and 4 newtons going to the left. Well, the 2 newtons going to the right is going to cancel out part of the 4 newtons going to the left. So you're going to have a net force of 2 newtons going to the left. Okay. So you can think of like the force on one side canceling out part of the force on the other side. So one goes the other way less. Okay, so in this case, it's unbalanced. We have 2 newtons plus 3 newtons is a total of 5 newtons on this one side because there's nothing to balance it. Okay, there would be motion and the scale would move. In this example down here, we can think of 4 newtons on this side, 2 newtons on this side. The scale's not going to tip as much because there's a little bit over here to cancel out the 4 newtons on this side, but it's still going to have an extra 2 newtons on this side. So it's not going to completely balance out. It's going to move based on this bigger one. And they can be equal in size and in the same direction. So these two forces can add together. This is like two identical people pushing on a car. So one person pushes with a force of 2 newtons, and the other person pushes with a force of 2 newtons. Their force adds together to make a force of 4 newtons. Okay? And it's kind of like this example here. One person can push on the car. If 2 people push on the car, their forces add together. If 3 people push on the car, their forces add together. So that's what we're saying here. This is like this. They push, and he pushes. 2 people's forces add together, and in this case, they would be pushing with 4 newtons. An important concept with these forces and motions is the idea of inertia. And inertia is any resistance to a change in an object's motion. So basically, objects want to keep doing whatever it is that they're doing. If they're in motion, they want to stay in motion. If they're not moving, they want to stay not moving. Okay? Often Newton's first law is called the law of inertia. So I put in the notes, it says an object wants to keep whatever motion they have or not have. So if it's not moving, they want to stay or remain stationary. So, this is why boulders and stuff just don't start rolling down a hill. They have a certain amount of inertia. They want to stay there and remain doing what they're doing, which is not moving. In order to get them moving and push on them, you need to overcome that inertia. If they are moving, they want to keep moving. So like if a car is going down the road, it has a certain amount of inertia. It wants to keep going in the same direction and keep doing what it's doing. So that tendency of it to want to keep going is what we call its inertia. Now, this also relates to safety. Seatbelts are an example of the law of inertia at work. If you're in the car and you're traveling along at 60 miles an hour, the car runs into something and it stops, your body has inertia. It wants to keep moving forward at 60 miles an hour. If you're not wearing the seatbelt, then your inertia says, I want to remain. I was moving at 60 miles an hour, and it says if they're moving, they want to keep moving. So your body wants to keep moving forward at 60 miles an hour. If you're not wearing a seatbelt, you move forward into the windshield at 60 miles an hour. Okay. If no unbalanced force is applied, they will keep their motion forever. So this is one of the things that when Newton was first talking about this, people really had a hard time imagining this because there's always unbalanced forces on Earth of friction that make things stop. But what Newton was basically saying is, well, imagine if there was nothing like friction to make something stop, it would just keep its motion forever. And places where we see this, particularly, are in outer space. So the Earth is in motion, it's moving, and it wants to stay moving, and it wants to stay moving the same way and at the same speed. There's no friction in space to slow the Earth down, so we just keep going around the sun, taking 365.25 days to make it all the way around the sun, and we never slow down, and we don't speed up, and we don't slow down and like have to fire an engine to speed us back up because years are starting to get longer. Okay, so we just stay in the same motion forever without friction. Objects with more mass have more inertia. So it's should be pretty logical. It's harder to stop a train than a bicycle. Or, for example, if 2 balls were coming at you, one of them was a ping pong ball, and one of them was a shot put, which is, a steel ball. It looks like a cannonball. They were both moving at the same speed. Which one would have more inertia? If it hit you, which one would want to continue its motion and keep going straight forward and doing exactly what it was doing? Well, of course, it would be a great big heavy shot put. Its inertia says it wants to just keep moving forward, whereas the ping pong ball, because of its low mass, would have less inertia, less of a tendency to keep moving in its same direction.
Newton's first law has to do with objects at rest and objects in motion. He noticed that objects at rest stay that way, until something comes along to move them. He also noticed that objects that are moving continue to move in a straight path unless a force slows them down and stops them.
Okay, so this is a good example of an object in motion stays in motion. Okay, so this kid sliding along on the ice, there's still some friction between the sled and the ice. If it was perfect, if there was no friction at all, and there was no air resistance blowing on the person, they would just keep sliding along forever at the same speed.
Newton called this tendency of an object at rest to stay at rest.
Now, this black ball is at rest, and it wants to stay in rest until it's acted upon by an unbalanced force. That's its inertia, its tendency to want to stay there and not move. Okay, when something hits it, that'll overcome the inertia. But it also makes sense that the more mass this ball has, the more tendency, the more inertia it would have to want to stay in that position, and you would need to hit it harder to get it to start moving.
And the tendency of an object in motion to continue moving, inertia. You must overcome inertia in order to start an object moving. And you must overcome inertia in order to slow down and stop an object that is moving. So Newton's first law of motion states that if no unbalanced force acts on a moving object, the object will continue moving at the same speed and in the same direction. And if the object is not moving and at rest, it will remain at rest until an outside force acts on it. A spacecraft will continue moving through space at a constant speed and in a straight path without the need for engines. Because there is little matter in the vacuum or emptiness of space, there is nothing to slow the vehicle down. Once the craft is away from Earth's atmosphere and its gravitational pull, the engines can be turned off. It will continue at a constant speed and in a straight path. Only if the engine is fired again will the craft be able to change speed and direction. On Earth, objects are affected by outside forces that slow them down and eventually stop them. Even on very slippery surfaces such as ice, objects will eventually slow to a stop. Friction is the force that slows things down. Here is an illustration of inertia.
Okay, now, all these plates want to remain at rest. They have a tendency to want to remain in the same place. There's a little bit of friction between the tablecloth and the plates, but if there's not too much, the inertia of these objects should keep them in the same place.
This tablecloth is loaded with inexpensive china and glasses of water. Now watch as we pull quickly on the tablecloth. Inertia is responsible for holding the china and glassware in place. Now, you may not want to try this at home, so here is a version of that same experiment, but only a coin, a piece of cardboard, and a glass are required.
Okay, now, the coin has a certain amount of inertia. It doesn't want to change position. It wants to sit in that same place. Right now, the coin has balanced forces acting on it. The cardboard is pushing up and holding it in place, and gravity is pushing down, so it's balanced. The weight of the coin is being balanced by the cardboard's ability to hold it up. When he pulls the cardboard out, the inertia of the coin is going to want to keep it in the same place. So it's going to want to stay right there floating in air. But now it's also going to have an unbalanced force, and gravity is going to pull it down in the cup. But the inertia originally is going to hold it in the same place in the center of the glass.
Your mother's good china is saved. Here's another demonstration of inertia.
So the mass depends on inertia. So the mass of this heavy boulder plus the rock mean that they don't want to start moving even when there's a force applied to them, because they have so much inertia. This man is able to pound this nail into the stick.
A large rock is supported on this person's head. A piece of wood is placed on top, and a friend proceeds to drive a nail into the wood. Why no headache? Inertia. The rock doesn't want to budge. It absorbs the force of the hammer blows, and the person underneath survives unscathed. Now, let's consider the inertia of an object that is moving. When you are riding in a car and the vehicle goes around a corner, you feel like you are sliding off to one side. But actually, your body wants to continue going straight as the vehicle turns. We can demonstrate this.
Now, watch carefully as this kid runs backwards. The ball is going to be sitting on the cart, and it's going to be going in a straight line backwards. The inertia of the ball means that it wants to keep moving forward and going and continuing its motion, even though the kid in the cart turns.
With this ball and hand cart. When the cart turns, the ball rolls off. Now, let's step back and see what is really happening.
The ball is moving forward. That's its inertia. It wants to keep going straight in the direction that it is going.
When the cart turns, the ball continues to travel in a straight path. So when you're in a car and it suddenly turns, your body really wants to continue in a straight line. A spinning gyroscope will resist changing its starting position. It can be balanced on a string or small stand. In the weightless environment of space, the gyroscope works even better. So inertia explains many common everyday situations.
We're going to stop here. You're going to answer these questions on your own, and then we're going to pick up from here next time. Hope you have a great day, and we'll see you again.